Okay. All right, tree diagrams, probably the easiest thing we will do. Okay, we're gonna go on page 137. Sure. Okay, so a tree diagram is a simple way of representing a sequence of events. Tree diagrams are particularly, man, I need more coffee, useful in probability since they record all the possible outcomes in a clear and uncomplicated manner. So our first example, Haymitch will wear either a white, purple, or yellow tie with a white, purple, or yellow jacket. Use a tree diagram to show how many different choices he has. Okay, so we're talking about his tie and his jacket. What are his options for colors of tie? White, purple, or yellow? Okay, he can also wear either a white, purple, or yellow jacket. So if he chooses a white tie, he could choose the white jacket, or the purple jacket, or the yellow jacket, not the bug. Okay, if he chooses the purple tie, he could choose either the white, purple, or yellow jacket. If he chooses the yellow tie, he could choose either the white, purple, or yellow jacket. So how many possible combinations do we have here? Or possible choices? 9, because you could choose one of 3 here, one of 3 there, and one of 3 there. 3 plus 3 plus 3 is 9 different choices. And there you have a tree diagram. So let me point out the things that are required. Okay, I do want you to write out the words on the first column and in the first set on the next one. So like you only have to write the words here once, write the words here once. From there you can abbreviate, and you do have to have the lines. So it makes it look like a tree. That's why it's called a tree diagram. Okay? What if the jacket and the tie cannot be the same color? 6 choices. Which ones are going to go away? White here, purple here, and yellow there, right? So let's make another diagram. No.
Could you just go along the first tree diagram and cross out?
You could, but these are 2 separate questions, so you need 2 separate tree diagrams. So 6 choices. Okay, this next example, the tree diagram, there's not really a ton of space for it. Okay, so you can put yours wherever you want. I'm going to write it under here on this paper because I can't write tiny and everybody see. So you can just write and abbreviate and do what you need to do to make it fit on your paper. Okay, so Katniss is at the cornucopia. She can get a square of plastic, a backpack, a bow, and arrows, or a tent. Then she can run in the opposite direction of Cato, Thresh, or Peta. Next, she can be allies with the careers or Rue. List all the possible outcomes. If it says list all of the possible outcomes, that is a tree diagram. That's how you know it's a tree diagram. If it just asks for how many possible outcomes, you can do a different method that I'll show you after this. But if it says list them all, that's a tree diagram. So how many different things am I talking about here? How many columns am I going to have? Okay, so she's going to have a weapon of some kind. She can run in one direction or another, and she can be allies. So we're going to have 3. So we're going to have a weapon. She can run away from. And then she has her allies. All right, so how many options for a weapon do we have? Yep. Obviously. She can have a backpack. With bow and arrows. Because it's all together. There's not a comma there, so we're going to let it be all together. All right, so she can run away from Cato, Thresh, or Peta. No way, there's not enough space? Only someone had warned you.
But if she aligns herself, doesn't Thresh not become a threat?
I don't know, I don't remember from the movie. I wasn't watching that closely, even though I watched it 4 times.
We haven't even watched half of it.
Yeah.
Oh, man. All right, and then lastly, she can be allies with the careers or with Rue. So for each one of these, we're going to have 2 more branches.
Oh, no.
I know, right? So is it always practical to make a tree diagram? No. But isn't it better than having to try to like figure out all of the possible combinations? What? Hold on to that thought.
I literally haven't even finished the first one.
They don't have to be perfectly straight.
They're not even close to straight.
I think you know at this point that there are lots of things that I don't care about when it comes to neatness. Okay. So how many branches do I have down here? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So there were 24 possible outcomes. Good morning, Heather. What?
That looks terrible.
Mine in here looks terrible too.
Yeah.
Just
Like a little bit, but not like all the lines are like, come on.
all right. So even though it's ugly, it's not hard, right? Make sure you put the title. Make sure you write out the words the first time. And then after that, you can abbreviate and make sure you have these lines. Okay? When using a tree diagram, the probability of a specific event can be found by multiplying, somebody said that earlier, multiplying the probabilities on the branches that make up the event. So suppose there are 2 lemons and 1 lime in the bag. If you pull out 2 pieces of fruit one at a time without putting one back, the probability changes depending on what you pick first. The tree diagram below shows those probabilities. Welcome back. So we want to know, what is the probability of drawing 2 lemons? So the probability that we first draw a lemon, and then again we draw another lemon. Okay, it's really hard to see, but these are the lemons up here, and these down here are the limes. Okay, so the probability that the first pick is a lemon right here is 2 out of 3, because there are 2 lemons and 1 lime. So 2 out of 3 for the first one, times the probability that the next one is a lemon is 1/2. So 2/3 times 1/2. Remember when we simplified these the other day? You have a 2 in the top and a 2 in the bottom, they can cancel. So the probability of drawing 2 lemons is 1/3. Okay, so tree diagrams are a great way to have a visual representation of all the possible outcomes, but sometimes there are too many options for a tree diagram to be beneficial, like the one we just did, right? So when that happens, you can instead use the fundamental counting principle. To figure out how many outcomes there are, which is a really big fancy way of saying multiply the options. Multiply the number of options. Okay. So it says use the counting principle to find the total number of outcomes in each situation. So the Hobb nursery has 14 different colored tulip bulbs. Each color comes in dwarf, average, or giant size. How many different kinds of bulbs are there? Okay, well there's 14 different colors times how many sizes? 3. 14 times 3 is 42 different kinds. Aren't you glad I didn't make you draw a tree diagram about the 14 different colors?
I would have started at 80.
Right? Started to. I like that you don't already hate me. I'll take it. Okay, so the type of bicycle prim once comes in 12 different colors of trim. There's also a choice of curved or straight handlebars. How many possible selections are there? How do I find it? 12 times 2, which is? So there are 24 selections. Okay, go ahead and do those last 4. If you get stuck on number 4, just skip it. We'll talk about it later. All right, turn and talk to a neighbor about what you got, and if you got stuck on one, and talk about what you got stuck with.
I got a three.
I mean, think about it.
Yeah, I did something.
But yeah, I probably
I got that.
how cold is
No, that might be wrong. I'm pretty sure that was.
It's supposed to be 82 today. Really? Yeah, no, she's gonna die.
Oh, yeah. Erica just-
Yeah, I wouldn't.
I didn't know.
One minute.
There's no way.
You ready to check?
No way. I was right. So we got, we're all wrong. Erica was right.
What? Nah, bro.
Barrett, which one were you correct on?
Oh, zero's not.
Barrett, which one were you right and they were
Number
wrong?
4.
Number
I got
4.
that one right. I had it wrong and then.
Yep.
Erica.
You have to read these kind of carefully because if it's 0 through 9, that's actually 10 digits. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So it's 10 to the 6th power. Did everybody get number 6?
At first I thought it was 6 because I did 2 times 3, but then I saw that it was 2 to the.
3rd power? Yep. Because each one of those coins can land heads or tails. So there's 2 options for each one. So 2 times 2 times 2, which is that 8. All right, are you feeling okay about these so far? All right, we're gonna play the lottery.
Yes.
We're gonna play the lottery. So everybody's gonna create their own lottery ticket. All right, I'm sad that no one won the lottery. Maybe next year.
And she said if you won, you get 100% on your side. Yeah. There was no, it's like a billion something, 1 billion event you win. So,
No one won. It was sad. You all have to take the test now. Events are independent if the occurrence of one event does not affect the probability of another event. For example, the probability of PETA being chosen did not affect the probability that Katniss was chosen, and vice versa. Therefore, they are independent events. Okay? So if they are independent, then the probability of A and B is equal to the probability of just A times the probability of just B. So we're going to do a lot with these spinners right here. So how many, what?
Who names their kid Foxface?
They didn't. That was just her nickname for her.
That makes a lot of sense.
Yeah, it was just her nickname. Okay, so how many outcomes are possible when you spin all 3 spinners? So this is that counting principle we just talked about. How many options do we have for the boys? 6 options for the boys. Times how many options for the girls? 5. Times how many options for animals? 3. What is 6 times 5 times 3? 90. So there are 90 possible outcomes.
So could this be considered exponential growth or is it inconsistent?
Too inconsistent. Okay, if you made a tree diagram showing all of these outcomes, how many branches would show landing on PETA, Foxface, and Mockingjay? Just 1. There's only 1 PETA, there's only 1 Foxface, and there's only 1 Mockingjay. So there would only be 1 branch showing that.
I feel like our brains have subconsciously been trained to overthink everything.
Probably.
literally.
Yeah.
All right. So number 3, remember that thing I was telling you about the notation? Like, I don't really care if you write it in this notation, but they're going to ask you questions like this. Okay. So what's the probability that PETA is chosen and Katniss is chosen? All right. So what's the probability for PETA up here? 1 out of 6 times, what's the probability for Katniss? 1 out of 5. To multiply fractions, you multiply straight across. 1 times 1 is 1. 6 times 5 is 30. So our probability is 1 out of 30. What's the probability of a boy being chosen on this spinner? What? 1 out of 6? I'm going to go with 6 out of 6. Because all 6 people on this spinner are boys. What's the probability that a girl is chosen? 5 out of 5. Well, you have a 5 on top and a 5 on bottom, a 6 on top and a 6 on bottom, so that just is 30 out of 30 or 1. So there's definitely going to be a boy. There's definitely going to be a girl. Okay. What's the probability that the first name ends with an H and the second name has 2 vowels? Okay. So look on here. How many of these names end with an H? 2 out of 6. What's a vowel?
Fox face.
A, E, I, O, or U. We're not worried about Y because none of these have a Y.
Two or more than
2 vowels, exactly. Exactly 2 vowels.
Oh.
Exactly 2.
more than
Nope, we're on the girls. This is going to be from the girls.
all right.
Don't they all?
Not
Oh.
She has 3, so not her. 1, 2, that one. 1, 2, this one. 1, 2, this one. 1, 2, that. She has 3. An O, an A, and an E. So 4 out of 5. Okay, you can multiply and then simplify, or you can simplify first. 2 and 6 are both divisible by 2. So I'm going to make that 1 and 3. 1 times 4 is 4. 3 times 5 is 15. So that's going to be a 4 out of 15. Okay, number 6, the probability that the first, or the boy name ends with a consonant. What's a consonant?
Not a vowel.
Not a vowel. And the second one lands on Rue. Okay, well, let's start with this one. It's going to be 1 out of 6 because there's only one Rue. Okay, look at the boys.
Is it 1 out of 5?
5, yes, thank you. Okay, of the boys, how many end with a consonant?
4.
Not Peta, Marvel, Fennec, Haymitch, Thresh, and not Cato. So 4 out of 6. Those are both divisible by 2. So 2 over 15. Okay, now we're adding in that third spinner. So now we're looking at all 3 of them. So what's the probability that the first one lands on Peta, the second one lands on Katniss, and the third one lands on Mockingjay? Okay, well, what's the probability the first one lands on Peta? 1 out of 6. What's the probability the second one lands on Katniss? What's the probability the third one lands on Mockingjay? So that's 1 out of 90, right? Okay, do those last 2. Okay, go ahead and compare with your neighbor.
number 8. I put 1 6 times it. It's the animals and traffic.
All right, let's check them. Should be 1 out of 45 and 4 ninths. How'd that go for you?
Pretty good.
Pretty good. Still feeling okay about probability in general? All right. Okay, next page. Or the inside of that page, I should say. If the probability of one event does affect the outcome of another event, those are dependent. So if A and B are dependent events, then the probability of A and B is going to equal the probability of A times the probability of B given that A happened. This line right here means given. Okay, that sounds really scary, but I promise it's not as bad as it sounds. So example 1, there are 6 black pens and 8 blue pens in a jar. Plutarch takes a pen without looking and then takes another pen without replacing the first one. So if he doesn't replace the first one, then the outcome of your second pull depends on what he chose the first time, right?
Haven't we not met in our test?
Isn't he the game maker?
He is in the second one.
Oh,
Yeah, he's the.
So we haven't met him yet. Haven't met him yet, sorry. Okay, what's the probability he will get a black pen and then a blue pen? So we want to know the probability that the first draw is a black pen and the second draw is a blue pen. Okay, well, what's the probability that the first one is black? 6 out of 14 times. If we're not putting the first one back, how many pens are left when we go to take the second one out? 13. And how many blue pens are in there? 8. So 6 out of 14 times 8 out of 13. These are both divisible by 2. So 3 times 8 is 24. 7 times 13 is 91. So the probability that the first pin is black and the second pin is blue is 24 out of 91. Okay? You might see it written, like this is what you're used to. You might see it written, the probability of choosing a blue pin given that the first pin was black. Those mean the same thing. So I would write that down, because if you see this on your homework, you're going to want to know what that means. Okay. Mags places the 7 cards above in a box. She draws 1 card, does not replace it, and then draws another card. Write both the expression and the answer here. Okay, so what's the probability that the first card is an N and the second card is an N? Okay, so before we do that, how many cards do we have? So 7 cards total. So what's the probability that the first card is an N? 2 out of 7. If we're not replacing it, how many cards are left for the second draw? 6, because we're only taking 1. Take 1 card out, so there's 6 left. And if the first one was an N, what's the probability that the second one is also an N? 1 out of 6. So those simplify to give you 1 out of 21. Okay, number 2, the probability that the first card is a C and the second card is an F. How many C's are there? 1 out of 7. Once you take that out, there's 6 cards left. What's the probability that it's an F? 1 out of 6. So 1 over 7 times 1 over 6 is 1 out of 42. Okay, go ahead and do those last four. All right, check with your neighbor.
Zero.
Stop hitting Yanni, quit.
I literally wrote all of them, and I forgot
You already got it. There's two ends though. Yeah. Oh, you missing. Only one is here.
You ready to check with mine?
Hey, you got light right. Let's go. Full.
All right, last thing we're gonna do. Actually, were there any questions on this? Any of them throw you?
Will there be one like 5 on the test?
Maybe.
Okay. Yeah. I caught it pretty quickly, but that's the kind of thing that would stop me for a long time on a test.
Really?
Maybe. When's the test, by the way?
May 4th.
Man.
May the 4th.
Oh, that's Star Wars Day.
Star Wars Day. Yep. All right, the last thing we're gonna do requires a little bit of common sense. I know. Okay? We're gonna tell whether each event is independent or dependent. Don't overthink them. Okay, so the first one, Haymitch is selecting a sweater and then selecting a pair of pants. Okay, does the choice of sweater really matter to the choice of pants? Okay, we're not overthinking it. We're not thinking about like Do they match? Or the colors? We're not doing that. Like, he's literally reaching in and pulling out a sweater, reaching in, pulling out a pair of pants. Does one affect the other? No, so those are independent. Okay, Madge, choosing one card from a deck, then choosing a second card without replacing the first. Independent or dependent? Dependent, why? It's like the third or fourth movie. Book. Second or third book. I don't remember. Is that the second book? Yeah, it's the second book. Okay. What makes you think that it's dependent? Yep, without replacing. Gail's wallet contains 2 $5 bills, 2 $10 bills, and 3 $20 bills. 2 bills are selecting without the first being replaced. Independent or dependent? Dependent. Why? Still haven't replaced it. Okay. Alma coin rolls 2 dice. Does the outcome of one affect the outcome of the other? No. So that is independent. Annie choosing 2 cards from a deck so that they make a pair. When you pull one out and you go to select the second one, does it matter what you chose the first time? I'm going to go with yes, because once you take one out, how many cards are left? 51, and you need one other to make a pair, so that is dependent.
Sounds like the person above us is mowing the lawn.
Yes, exactly. Okay, we're going to do the rest of this in that next page of notes on Wednesday. Okay, so I'm going to stop there. Now,